Any time have you observed fluorescence anywhere? Microscope. So you have a fluorescence microscopy that you have observed. Very good. So what does fluorescence microscopy do? I mean, what does it do? Or what is fluorescence per se? Okay. Okay, so you have seen some microorganisms that fluoresce under the microscope, right? So, but what is fluorescence? If I ask you what is the process of fluorescence, can anyone answer? Okay, so there is an emission of light, right? So far when we were looking at dyes which were colored molecules, right, there was no emission per se, it was just absorption of energy to go from the ground state to excited state. Now in fluorescence what you are going to see is they are going to go from the ground state, go to the excited state and then come back emitting some light, right, and that energy is going to be given by the in the form of light. What else, like what objects do you see around you that are fluorescent other than microorganisms? So there are some microorganisms surely that fluoresce, but there we all use so many objects in our day to day lives that, so radium is not per se fluorescence, okay, it's something called as a phosphorescence. So most of the radium sticks that you see, they for example those radium stickers that used to come in the market, right, and they are able to give you light even after the light is switched off, right, like the white light is switched off, even after that for a longer time, 2-3 hours you can see those fluorescent, those tiny fluorescent stickers, right. So that those kind of things are under, they fall under phosphorescence. Any example of fluorescence? Okay, so why don't we take this as a question, as a post lab question. I want you to think about where all do you see fluorescence in day to day life, okay, and please when we discuss post lab questions, right, come with examples, so we can discuss whether they are fluorescence or phosphorescence or some other phenomena, right. So tomorrow we are going to see something else called as chemiluminescence. Okay, chemiluminescence is another phenomena in which light is produced or energy is given out in the form of light, but it's not because of absorption of energy and, like, you know, the typical way ground state to excited state, that doesn't happen, but the energy is given out because of a chemical reaction. So the heat in a chemical or the energy in a chemical reaction typically more often is given in the form of heat, but in this case it will be given out in the form of light, right. So there are various forms in which you see fluorescence, phosphorescence, chemiluminescence, you know, all of these things. So I want you to think which ones amongst these are fluorescence, okay. So remember there are ground state, we have always been talking about electrons in the ground state, they get excited to the higher energy excited state. So there is not just one ground state, there is like a layer of, or you can say multiple ground states are there which differ in the energy a little bit, right. And also in the excited state there is not just one excited state, there are also multiple excitation states possible, okay. So when an electron from ground state gains energy, right, and gets excited, so let us say this gets excited to the excited state S3, okay. Now this particular electron, what it is going to do is, typically in most molecules it will just come back, okay, it will just come down to the ground state without radiating any energy or non radiating in any energy in the form of light, right. So it is just going to come down in a non-radiative transition, that is what they call it, okay. So non-radiative transition meaning it just went up, it absorbed some energy, then it came down after some time, right. Now in fluorescence what happens is, this electron in a higher excitation state comes down to the lowermost excitation state. Does that mean, like, out of these excitation state, S1 which is the lowest in energy, that is where that electron is going to come down. Okay. And from there what is going to happen is it is going to come down again. So, it is going to spend some time there, okay. It is going to spend some time at S1 and then come down, okay, instead of directly coming down. So, let us say you are jumping on the 4th step, instead of directly jumping down on 0, what you are doing is from 4 you are coming down to 1 and then staying there for some time and then coming down on 0. Okay. So, that is what is happening in fluorescence. This jump from S1 to S0 is more often, you can see some kind of light or some amount of energy is emitted in the form of light. Okay. This is different from the dyes that we had seen. How is it different? There it directly goes up and then from HOMO to LUMO and then it comes down, right, and that is a non-radiative transition. Now, when we think about, so this is fluorescence, okay. Typically all of this happens in a very quick time. So, this happens in like 10 raised to minus 15 seconds or so. So, the time scale of fluorescence is very, very short. Okay. So, that electron is going to go up and then come to S1, go to S3, S4, come down on S1, again comes down to S0, is going to happen very quickly in around 10 raised to minus 15 seconds. Sometimes what happens is you have an electron, okay, and that electron from the ground state gets excited to S3, okay, let us say, then it comes down to S1. Okay. What then it does is, it somewhere in the middle it forms a much more stable triplet state, like it will come down to that triplet state and then it is going to come down. Okay. So, do you see the difference in these two processes? One is directly it is going to come down in the singlet state. In the other case, what it is going to do is, it is going to come down, be stabilized in a more stable triplet state. So, it is a much longer time that it is spending, like as compared to this process takes much longer because triplet is very stable. So, it can remain there and then come down. Okay. So, this kind of transition is typically a phosphorescence. Okay. So, we do see objects around us, okay, which give or emit light, right. So, some of them are fluorescent, some of them are phosphorescence, it depends on the time scale mainly. Okay. Phosphorescence can go even like a couple of seconds or 10 seconds is I think the maximum phosphorescence. So, the process here I said 10 raised to minus 15 seconds, this can range anywhere from a few seconds to 10 raised to minus 3 seconds to like 10 seconds or so on. It is a large time scale for phosphorescence, okay, it takes longer. So, today what we are going to do in lab is we are going to produce a molecule called as fluorescein. Okay. Now, fluorescein is one of the most abundant molecules used for the purpose, like the purpose of fluorescein is to exhibit fluorescence, right. So, what people have done is they have now formed various derivatives of fluoresceins, meaning they have changed some functional group and here and there, right, and then they have formed a new molecule which can be attached to something else. So, for example, you can tag a protein in the body with this fluorescent marker and then it will do what you are able to visualize what chemistry it does inside the cell. Okay. So, you can have proteins tagged, you can have DNAs tagged, various organelles inside the cells can be tagged with a fluorescent moiety, right, because remember the organelles are not fluorescent. So, you have to attach something that will give you some signal, right. So, what happens is when you attach it to the organelle, you can then track its movement, or let us say you have a new drug, right, that drug can be fluorescently tagged so that you can see where it goes to which, is it really targeting DNA or is it targeting proteins or is it targeting mitochondria, you know, like if you are creating a drug that specifically you want it to target a particular organelle, you can attach. So, it is basically a signal, it is a way of giving you some kind of signal, right, such that when this shines you can see that that particular drug is, how is it moving inside the cell, or let us say even in a whole or a animal, or you know, typically we do these studies in mice, right. So, you can see where the drug ends up in the animal using a fluorescent tag, right. So, fluorescence is not just used in day to day life for, again you are going to give me those examples. I expected some examples from you, because this is such a common phenomena, right, that next time you see fluorescence you need to think which ones are the really fluorescent applications of fluorescence. But this is one of the applications wherein you can use it for medical purposes, you know, like medical research uses it a lot, biochemical research, biochemistry, drug development, all of these fields are going to use fluorescence a lot to study how these drugs or different proteins interact with each other. Okay. So, the other way in which we used fluorescein is, remember fluorescein was typically used, or it found its use in World War II. Okay. So, what was the use in World War II? Because at that time all of these other fields like medical research was not so prominent, it is now prominent these days, right, post World War. But what used to happen is, German pilots, let us imagine that you are kind of flying over the Pacific and or Atlantic. What is going to happen is, your plane may be shot down by enemies weapons, right. So, it may be shot down and you are now in the ocean. You are a pilot kind of struggling to survive in the ocean, you have some debris left. So, you expect that a rescue team can come and rescue you or see you in the ocean. Now, what is going to happen is, in the ocean, it is a vast ocean, you can't really tell the coordinates. So, all of this is going to happen in the case of chaos, right, that entire plane being shot down, there is no way to tell the rescue team that I am here and here inside, you know, in this vast ocean. So, what they used to do is, they used to carry a small vial of fluorescein with them, okay, and they released it in water as soon as the plane shot down. So, what used to happen is, the entire patch became fluorescent. So, if any rescue plane is flying around, they can quickly locate that plane and then rescue the pilot. So, that is how the main use of fluorescein per se came into existence. There are couple of other uses. Okay. So, as I told you, it can be detected very nicely in water. So, you can think of some other uses, right. So, if I tell you that it is able to detect water, right, the next logical use is, it can be used in detecting where there is a leakage in pipeline. Right, long pipelines, if you want to really detect where the leakage is, you typically add a dye, okay, and then you see where that dye emerges up, right, and then you can track that this is where the pipe is leaking. Okay. Then couple of other uses of fluorescein are in in medicine, of course. When your cornea, anybody has had a scratch on their cornea ever? It's very painful, but what happens is, again it is very difficult to see where that scratch is in your eye, right, for doctors, or whether there is a scratch or not. So, what they do is, they again add a derivative of fluorescein that is used as a dye in your eye, so that they can see that scratch very nicely. Okay. So, I have told you some uses of fluorescein. Now, in your post lab questions, as I told you, I need some day to day applications of fluorescence and also some uses of fluorescein. Okay. Now, let us look at the reaction that we will be doing today. Okay. So, what we are going to do in lab today is, we are going to use, what is this molecule? You have used it already, resorcinol, and anybody knows this one? phthalic anhydride. So, we are going to use these two and some kind of acid. So, we are going to use H2SO4, concentrated H2SO4, we are going to be dealing with concentrated H2SO4. So, please be careful, okay, when you are adding H2SO4, do not rush around. Okay. So, what we are going to do is we are going to add these two and without a solvent. So, this is a solventless reaction. Okay. They are going to fuse and melt together to form fluorescein. There is no liquid state in this, it is a solid. So, solid phthalic anhydride and solid resorcinol will melt together, fuse together to form fluorescein in the case of in presence of H2SO4. Okay. So, let us go quickly over the mechanism. Okay. So, now when we see something like this, what thing first comes to your mind if I show you all these three things together? So, when I have an acid, what is going to happen? Dehydration will happen, but not right now, right? Because remember this OH, it is very difficult to dehydrate resorcinol, for example. It is an aromatic molecule, aromatic, or you know, it is very difficult to dehydrate resorcinol or phthalic anhydride. Anhydride is already without a water molecule, right? How do you create anhydride? Acid loses one water molecule, right? Two molecules of acid lose one water molecule to get you anhydride. So, it is very difficult to dehydrate any of these. So, what should happen in my first step of reaction? So, what will attack what? Okay, so H plus meaning it does not have any electrons, right? It is a proton, right? Protons do not attack anything, protons get attacked, right? Because you need electrons to attack, right? What do we say? Electrons attack a proton, right? The arrow always goes from a electrons or negative charge to the positive charge, right, or vacancy. So, in this case proton will not attack anything, but it will get attacked. Now, what in my molecules will attack that proton? Which oxygen? There are so many oxygens here. So, there is this oxygen, there is this oxygen, then there are these oxygens. Which ones will get protonated? Which one? Phthalic anhydride, which one? So, how many of you are saying it will be the double bonded oxygen that has a higher chance of getting protonated? 2 people. How many of you are saying the single bonded oxygen? So, you are nodding your head for both. So, what is happening? You are confused. Okay. So, let us think of it this way, right. So, whenever you are confused, okay, here is something to do is try protonating either one and see what structure is forming. Okay. Whenever you are confused, I always think the reaction that kind of goes forward is always going to be something that will give me a resonance structure to make it stabilize, right, the product, for example. There is a possibility of this. Right. Now, which one amongst these two has a resonance structure? The first one. Okay. So, that is a little more stable than the second one. Everybody agrees with that? Okay. I am not saying that second one does not always happen. Okay. It is not like a complete no-no, but if it happens, it is going to quickly lose that proton to go back to this. So, remember acid base reactions are going backwards and forwards. So, something that gets protonated can also get deprotonated back to give you the starting material, right. So, out of these two, which ones do I choose? First one, because it has a resonance structure, it is a little more stable. Everybody good? Typically, between a double bonded oxygen, a carbon, the carbonyl oxygen and an oxygen that is, you know, something like in the form of anhydride or acids, the single bonded here. the non-carbonyl oxygen, it is always this one that gets protonated, or this one that has a higher basicity or higher ability to attack a proton. Why is that? Because that oxygen is pulling those electrons away from that carbon with both hands, like it is a double bonded one, right. So, it is pulling with both hands. What is going to happen is it has a higher electron density to attack. Okay. So, anytime you are confused, think about all these things to get to the answer. Okay. So, I have this now, let us get rid of this one, right. So, what will happen next? Okay, so there is a resonance happening, there will be a positive charge here, right, positive charge on the carbon, there is also one more resonance structure where that oxygen donates electrons here, right. There is a lot of resonance happening, this molecule is quite stable, but what will happen next? Somebody told me to slow down my reaction mechanisms, I am going to slow down as much as possible now. So, tell me now what should happen. Look at the, everybody has the manual. What is the final structure? What bonds do you see formed? It looks very confusing, right? The molecule, how do I get to that molecule using these two, right? It is not a straightforward reaction that you have seen. So, what do you think? So, again you have created a positive charge, right? What should attack it? Something with a negative charge or something with electrons, right? Where are the electrons in this whole system now? The carbonyl has electrons, but you have already now protonated it, right? So, much less likely that it will attack itself. Resorcinol, where are the electrons in resorcinol? So, the OH has electrons, what other part in resorcinol has electrons? The benzene ring, right? You have typically seen in an electrophilic aromatic substitution reaction, some of you were trying to do the mechanism in dance yesterday. What happens in electrophilic aromatic substitution? The pi electrons of benzene are going to attack the electrophile, right? What we have created here is an electrophile, because we have created a positive charge. The pi electrons from this benzene ring or resorcinol ring for that matter is going to attack that positive charge, right. So, in the next step what I am going to do is attack it here, open this up, okay. Is everyone with me? What am I missing? Right? Everybody good? Simple step of electrophilic aromatic substitution, first step. Okay. Now what should happen? What should happen next? So, there is a positive charge, right, which we do not like much, right. This is a non-aromatic system. So, from aromatic system we have gone to a non-aromatic, right. So, it is not good. It does not want to stay like that. What happens in an electrophilic aromatic substitution reaction as the second step? So, dehydration, or rather it is going to give up, it wants to recreate this double bond, right. So, it will give up a proton right? Some base in the solution is going to come back, attack and reform this double bond, right? I am just going to say B minus. Okay. Is everyone with me? Okay. So, let me just copy paste this thing into the next one, so that we have more space. This is going wrong. Okay. Anyways, so we can start from here. So, what is going to happen in the next step, right, is this OH. So, again think logically what should happen next. Sorry, did I draw something wrong? I think I bonded it to, that is what I think I bonded it to the wrong carbon here. The structure is itself wrong. Just give me 1 minute to redraw. Right, now we are good. Okay. So, what will happen next? Did I? Sure. Okay, okay, yeah. Yeah. So, what should happen next? You are in acidic medium. Again think of it this way, you have added, you are constantly in acidic medium, right, concentrated acid is there. This base is pretty much like what the water molecule you have is going to act as a base, right. There is not much base in the solution, it is concentrated acid. So, what should happen next? Double bonded O, what will it do? So, it can grab a proton, that is one way. But think about your final product. Again, always when you are writing the mechanism, always think about what the final product you want to form, because you want to write down the mechanism towards that final product, right. So, in this case what is going to happen? Okay. So, you have this OH, right, it can also get protonated. Okay. Should we protonate that? So, let us quickly make it to OH2 plus. Okay. Now, when I make it to OH2 plus, what happens typically? It will leave, right, because it is now a good leaving group, it is a water molecule that will be eliminated, right. So, let us look at it this way. So, what I am going to do is, I am going to make it leave, as a result of which what happens? There is a positive charge there. Okay. Now, what is the stoichiometry of the reaction? one molecule of acetic phthalic anhydride is reacting with, look at the reaction, look at the final product. Is it 1:1 or 1:2, right? So, one molecule of phthalic anhydride is reacting with 2 molecules of resorcinol, right? So, what do you think will happen next? We have added only 1 molecule of resorcinol till now. In the next step, what is going to happen is another molecule of resorcinol is going to attack this species. Now, where will it attack? The positive charge, right? Everybody with me? So, what we are going to do is, in the next step, okay. Now, I am going to stop after this step, okay. I do not want to give you the entire reaction mechanism just like that. So, what you are going to do is, when we go back to the post lab questions and we discuss it tomorrow, think about, somebody has to come to the board and explain this mechanism just the way what I am doing right now. Who will do that? Who is going to take up this challenge? Come on, it is okay. Anybody wants to take up that challenge, I will help that person, definitely. We can discuss the mechanism today, that person has to come to the board tomorrow and explain it for us. Somebody wants to? Come on, it is not that difficult. What we are doing is just arrow pushing, right? Electrophilic aromatic substitution, there is nothing else. Somebody? Or then I will have to choose, that is the thing. You want to do it? Okay. So, we will discuss the mechanism today. All of us can also discuss this, okay, discuss it within yourselves, but what's going to happen is, this resorcinol molecule will attack it here, okay, and then you have to think what will happen next. So, this is almost like 3/4 of the mechanism done. Now, it is only one more step remaining. That is where I am telling you to think about the mechanism, what should happen next, okay. Is everyone good? Okay. So, now what I thought is, we can, if we can, maybe we can play a video of the experiment itself. Better? Better?
Hello again. Imagine yourself to be a pilot, but an unfortunate one. Your plane has downed in the Pacific Ocean, but you managed to escape just in time. But in this vast ocean, how is the rescue team supposed to spot you? Germans during the World War II came up with this novel idea to use the compound called fluorescein, which when dissolved in water exhibits fluorescence and emits a bright green light to attract the attention of air-sea rescuers. Fluorescence is the phenomenon in which a compound absorbs energy in the form of photons and then re-emits the energy in the same form. Fluorescein exhibits pH-dependent fluorescence, which means that the light it emits depends upon the pH of the solution. In what pH conditions do you think that fluorescence increases? Acidic or basic? While you think about this, let's see how fluorescein is prepared reacting phthalic anhydride and resorcinol. For the experiment, we will need first, let's take a round bottom flask and add our two reactants, phthalic anhydride and resorcinol. We now add a few drops of the catalyst, that is, concentrated sulfuric acid. Now, let's set up the reaction apparatus. Now,
okay, so in the reaction apparatus, what do you see? Is that there is a condenser pump, okay. Again, because we are using a lot of no solvent, there are a lot of fumes that will come out, right, it is a fusion reaction. So, I mean, it is a solid state that these two compounds melt, they are going to give out some fumes, right. So, what is going to happen is, we have to make sure that we put a condenser. We are also going to make sure that the condenser is fitted right. meaning the water should go in from where? From down and comes out from the top. Okay, and we are going to use a water pump. So if you see on in our labs, there are no like sinks to drain water. So what we are going to do is, we are going to take a bucket, put a pump in it, and that pump is going to circulate it. Okay, so the water that comes out is also going to go in after some time, right? So it's a total circulation. What she is doing is, she has added phthalic anhydride and H2SO4 and resorcinol together, added that condenser attached. Now here it is important to use grease, because we are going to heat it at a high temperature. So we do not want it to get fused. Okay, so we are going to use some grease.
Let's heat the reaction mixture in a heating mantle until it becomes dark red and viscous. Since we are going to heat this at a high temperature, the reaction mixture might get evaporated. To avoid this, we use a condenser. The condenser works by circulating cold water through a tube, which cools the vapors and converts them back to liquid. We use a pump for this circulation.
Okay, so closely observe the setup.
We will then cool the reaction mixture to room temperature.
Okay, so this is going to be very hot. Okay, so what we are going to do is, we are going to slowly remove the heating mantle below it and just keep it like that until it comes to room temperature. The next step asks for us to add cold water. Now if you add cold water to a very hot setup, it is going to break. So what we have to do is, we have to make sure that it has come down to room temperature, then only we are going to add water to it.
Now let's isolate the dye in powder form. For that, let's dissolve the dye in 35 ml of water.
So we are going to add the water
Then
from the top of
we will heat the contents to completely dissolve the dye. Let's cool the flask to room temperature and then separate the product using vacuum filtration. If there is some product stuck to the round bottom flask, we can wash it off using cold water. To observe the fluorescent properties of fluorescein, let's take the prepared fluorescein in a test tube and dissolve it in water. Fluorescein absorbs maximum intensity of radiation at 494 nanometer of wavelength, which lies in the ultraviolet visible range, and emits radiation in the visible range. Therefore, when kept under a pure source of UV light, the fluorescein solution starts glowing. When potassium hydroxide is added to the fluorescein solution, the glow becomes brighter. So now it is clear that fluorescein emits more light in the basic conditions than in the acidic conditions. This is because the anion formed at basic pH is highly conjugated. Fluorescence.
Okay, so in the acidic condition, it is going to remain like this, right? But in the basic condition, you have two groups OH and COOH, right, which the base is going to deprotonate and form an O minus here, right. Once you form this O minus, this oxygen's electrons are way more, it is easier for this oxygen to delocalize its electrons into the ring, right. So remember, we were talking about conjugation, right, and how it increases as you add the number of double bonds or pi bonds into the system. In this case, it is increasing because you are able to delocalize a negative charge into that pi bonds, right. So you are going to delocalize the charge on the entire aromatic system. Okay. Now what happens, because of which under basic pH, when we add KOH to the system, what we are going to see is, it is going to fluoresce even brighter. Okay. So today what you have to observe is how fluorescence is a pH dependent phenomena for fluorescein. Okay.
is the in thing nowadays, be it to tag DNA or proteins, to detect corneal abrasions or intraocular tumors. It is also used to detect oil leakages and of course air sea rescues. Fluorescein was also once used to impart a green color to the Chicago River on St. Patrick's Day. Pretty cool, right? But on the protests of environmental activists, it was replaced by a similar biodegradable derivative. We hope that now you understand the chemistry behind fluorescein better. Thanks for watching.
Okay, so this was another student made video of fluorescein. Okay, so what we are going to do, everything is clear, like the procedure is clear. Add 3 things, add the condenser properly, let it run or let it heat for 10-15 minutes. Once that brownish liquid forms at the bottom, you are going to cool it first to room temperature, then add water around 35-40 ml, right, and then you are going to get a powdered form dye. Okay, the dye looks red in color, right, it is not fluorescent, but when you put it in water, then it gets fluorescent. So what is the reason behind this? So that also something you should tell me. Okay, why is it not fluorescent just like that? It looks like a powder, red powder, but when I put it in water, then it starts fluorescing. Okay, so these are all the questions we will discuss in the post lab questions. Okay, everything good for today? So yesterday you submitted your DBA, right? Now today you are going to submit your diazotization reaction, okay, in the afternoon. So what's going to happen is, in the afternoon we have some time free, so use that time to complete your lab notebooks, okay, so that you have some more time, okay.